Hey, this is Mr. Ayton. Welcome back to Pre-AP Chemistry. This is Unit 1, Atomic Structure, but it's Week 2 we're getting into. And we're getting into a little bit more chemistry action here, where we're going to be taking a look at electron configurations, a thing called PES, Photoelectron Spectroscopy data, as well as the photoelectric effect equations of wavelength, frequency, and energy. So let's get to this Week 2 of Atomic Structure. If you remember the Schrödinger or wave model, the electron cloud model, it's given us the probability of where the electrons are. You can see the electrons are moving at the speed of light. We don't know exactly where they're moving, but we know they're moving in what we call orbitals of the greatest probability. And that's what electron configurations do. Electron configurations, the purpose of them, it's a clear and concise representation of the arrangement of electrons around the atom's nucleus, okay? And just stay with me real quick. You can see on the left-hand side of our periodic table, we think of our what we call energy levels, principal quantum energy levels. You can see this is the n equals 1 principal quantum energy level, the n equals 2, the n equals 3, the n equals 4, the n equals 5, so on and so forth, okay? Now, our periodic table is grouped in orbitals. So you can see this is the s orbital. This is the s orbital. The s orbital is the simplest of all the orbitals. You can see right here is called the p orbital, And right here in this big group right here is called the d orbital, And so we're going to be grouping our electron configurations in terms of these orbitals. So let's start with the simplest atom, which is hydrogen. Hydrogen has 1 electron, okay? So that electron would be located in the 1, principal quantum energy level 1, s orbital, and there's 1 electron in that orbital, okay? So we call that 1s1. That's its electron configuration. When we come over here to helium, helium should really be kind of over here in terms of electron configurations. Helium should be over here. So helium is in the principal quantum energy level 1. It's in the s orbital, but there are 2 electrons. There's 2 electrons, and that accounts for both electrons of helium. So helium's electron configuration would be 1s2. 1s2. So now let's come over to lithium. Lithium, you can see, is now in another what we call principal quantum energy level. Lithium has 3 electrons. We have to account for where all 3 of those electrons are. Well, we know 2 of these electrons are counted closest to the nucleus in the 1s subshell. So it's 1s2, that's where the first 2 electrons are, and then the outermost electron is 2s1, okay? Beryllium right here, beryllium has 2 electrons in this second quantum energy level. There's 2 electrons that are closest to the nucleus in 1s2, and then there is 2s2. So that is its electron configuration for beryllium. 1s2, 2s2, you can see 2 plus 2 is 4. That's where the 4 electrons are accounted for. Now let's come over here to boron. Boron has 5 electrons. Remember, there's 2 in this 1s orbital, so 1s2. There's 2 over here in the 2s, so we call that 2s2. And then it's in the n equals 2. It's in the p orbital, but there's only 1 here. Count up those numbers. 2 plus 2 plus 1 is 5. That's the 5 electrons for boron. So boron's electron configuration would be 1s2, 2s2, 2p1. Carbon would be 1s2, 2s2, 2p2. And then nitrogen would be 2p3. Oxygen would be 2p4. Fluorine would be 2p5. And neon would be 2p6. Obviously, you can see I'm not writing in the 1s2 and 2s2, but those account for everything as we go over here. So if we looked at neon, which is right over here, neon, his electron configuration would be 1s2, 2s2, 2p6. Okay, let's come over to sodium here. Sodium now has 11 electrons. So there's 2 in the 1s, so we got 1s2. We filled up the 2s2. We filled up all of this in 2p6. And what does it end in is 3s1, which means, yes, look at something like potassium. Potassium would end in 4s1. and then 5s1, and then 6s1. These would all end in these electron configurations. Obviously, what would something like magnesium end in is 3s2, and then 4s2, and then 5s2, and 6s2. You can see that it's the principal quantum energy level, the orbital, and how many electrons are in there. Well, what about something like aluminum? Aluminum's all the way over here. You can see we have 1s2, 2s2, 2p6, 3s2, and we end in 3p1, which means this ends in 3p2, 3p3, 3p4, 3p5, and 3p6 there, 3p6. And that ends all the way, which means, yes, something like krypton would end in 4p6, and then 5p6, and 6p6. And so we would know what those would end in just because of where they're located on the periodic table. Well, when we get to the d orbital, well, let's come over here to potassium. Potassium, what would potassium's electron configuration be? Well, we would have 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s1, so on and so forth. Well, when we get to the d orbital, you can see the d orbital right here. Something like scandium. Scandium is in the d orbital. Well, what would scandium's electron configuration be? We would have 1s2, 2s2, 2p6, 3s2, 3p6, because those are all filled, and then the 4s2, but scandium comes down to 3d1. Okay, so this is 3d1, which means 3d2, 3d3, all the way up to 3d10 right there, all the way up to 3d10. And you can see there's 10 total electrons in the d orbital that can be put in there. 3d10. Why does it go back to the 3d? Because you can see it's easier to fill in these 4s's before the 3d. So this would end in 4d1 and 5d1 and so on and so forth. Okay, so those are electron configurations. Now let's go to what's called our photoelectron spectroscopy data. Okay, photoelectron spectroscopy data, just like mass spectroscopy, dealt with isotopes and mass. Photoelectron spectroscopy deals with electron configurations, and it tells how much energy, what we call binding energy, the energy that's bound because those electrons are attracted to the nucleus. And the nucleus is attracted to the electrons, but it's attracted to the nucleus. And so the closer the electrons are to the nucleus, the more binding energy they will have. And you can see, so binding energy is how much energy it would take to remove that electron. The relative number of electrons is how many electrons you have. So you can see this one here, there's 2 electrons, which means that would be the 1s2. Why would it be the 1s? Because the 1s is closest to the nucleus, which means it's the most attracted. It would take the most energy to remove, and so that's the 1s2. Now you can see the height of this is only 1, which means that would be 2s1, wouldn't it? 1s2, 2s1. So what element is that? 1s2, 2s1. That is right here. That's lithium. 1s2, 2s1, 3 total electrons. You can see which electrons would be most easily removed is the ones on the outside, which we call the valence electrons, because it takes the least amount of energy to remove this electron. It's least binded to the nucleus. So let's take a look at another example. Always start with your highest energy, and that's obviously going to be the 1s2. You can see this is a height of 2, so 1s2, 2s2, which after the 1s2 and 2s2, if we come back, we go 1s2, 2s2, then we go to the 2p's. Then we go to the 2p's. So this would be 2p. How many electrons will we have? 1, 2, 3, 4. 2p4. So count up those electrons. 2 plus 2 plus 4 is 8 total electrons. What is 8 total electrons? That would be oxygen. That would be oxygen. And you can see 1s2, 2s2, 2p4, that's the element right here. That's oxygen. That's oxygen, okay? Let's go to one more example of our photoelectron spectroscopy. Start with the highest amount of energy. We have 1s2, then we go to 2s2, then we go to the 2p, right? And how many do we have? 2p6. That means we're totally filled so far. Then we go after the 1s2, 2s2, remember 1s2, 2s2, 2p6, go to the 3s, go to the 3s. So we have 3s2. What's after the 3s2? We have 1s2, 2s2, 2p6, 3s2. Then we got the 3p's, don't we? We got the 3p's. So we're going to go 3p1, 3p1. What element is that? Well, that's aluminum. That's aluminum. Because aluminum would have 2 plus 2 plus 6, that's 10, plus 3 more is 13 total electrons. Which electron would aluminum lose first if it had to lose electrons? The one with the least amount of energy. You can probably see how many total electrons aluminum could lose. It could lose 1, 2, 3, and it could be a positive 3 charge if it loses these 3 electrons. You can see it's not going to lose any from the 2p6. It can if you have enough energy, but it will tend not to because it's a lot of energy to remove these electrons right here. And that tells us, that goes to our photoelectric effect equations, okay? So let's say to lose the first electron here, let's say the energy is 0.980 times 10 to the negative 18th joules. That's how much energy to remove that first electron. If we want to know what would the wavelength of light be to remove this electron, what wavelength of light would have enough energy for this? We're going to use our photoelectric effect equations, which means we're going to be using E equals h times frequency. So our energy is 0.980 times 10 to the negative 18 joules. What is h? H is Planck's constant right here. 6.626 times 10 to the negative 34th joule seconds. And that is times by our frequency. So you could find out the frequency of this by just dividing. And we get 1.48 times 10 to the 15th hertz. Okay. Then we can use the speed of light equation. The speed of light equals wavelength times frequency. The speed of light is 2.998, or 3 times 10 to the 8th meters per second. And we know our frequency is 1.48 times 10 to the 15th. We calculated that. And we can know the wavelength. And the wavelength of light for this is 2.03 times 10 to the negative 7 meters. You're going to need a very small, probably something in the ultraviolet region to eject one of these electrons. Now, if you remember back to physics, we combine these two equations to be equals hc over my wavelength, or wavelength equals hc over the energy. And that is kind of a combined way to do this two-step problem into just one. Well, that is week 2, unit 1, atomic structure. Hopefully that made sense. You might have to watch it more than once about that electron configurations, but it was pretty exciting. I'll talk to you guys in class. Bye.